3-bit asynchronous up-down counter design. In this asynchronous up-down counter, what we try to do is we try to look for what exactly the circuitry that we need to build such that it can count up or count down based on your selection. So there should be one extra input to choose the mode. Okay, that mode can be M or that mode can be up. Okay, as you like, we can take one extra input, and from that we are supposed to control. So in the question itself, this is the requirement. We are supposed to design 3-bit asynchronous up-down counter. So as the number of bits are 3, obviously what we need is we need 3 flip-flops. So 3-bit asynchronous counter. For 3 bits, 3 flip-flops required. That's fine. Let's use 3 flip-flops. That's fine. Next, what we need to do? What we need to do is we need to look at state diagram. Let's do the state diagram. Then we will see the input-output relations, and it is a full counter. We need not look into reset logic. We need not stop in between for a synchronous counter. If at all you want to stop in between, you can stop it, but based on the mod number. Maybe if it is mod 10, mod 20, okay, based on that. Okay, if it is not a 3 bit, if it is a 4 bit or 5 bit, something like that, based on the count value, it can be 3 bit also, but the count value will be less, maybe 5, 6, something like that, 4, 3. Okay, so based on the number of bits that we are using, based on the mod n value, we may use some reset logic to stop in between. Of course, that is optional, that we are not going to do here, but it is part of the procedure. We will draw the circuit, we will look at the timing diagram. So what we try to do is, now first we try to draw the state diagram. So state diagram is little, instead of drawing 2 times same state diagram, what we can do is we can incorporate everything in a one single state diagram that I am going to show it to you. Okay. So what we try to do is, let's use mode M. When M is equals to 0, down counting. When M is equals to 1, up counting. No, you don't want to use M. Earlier we have used up. When up is equal to 0, down counting. When up is equals to 1, up counting. Okay. Either way we can use. Let's use up. Earlier we have used up, right? So we'll do that. So what I try to do is just it will go from one state to the other state. Okay. So initially it will be 0, 0, 0. How many bits? Only 3 bits. Okay. So what we try to do is when 0, 0, 0, of course. So I'm trying to show that when up is equals to 1. When up is equals to 1, it will going from 0, 0 to 0, 0, 1, 0, 1, 0, 0, 1, 1. So this is when up is equals to 1. Then it will go to which state? 1, 0, 0. Then 1, 0, 1. Then 1, 1, 0. Then 1, 1. So what is going to happen is this to here it will go. Then this exactly transition takes place when up is equals to 1. When up is 0. So when up is 0, what exactly that is? This is what exactly the case. When up is equals to 0, it will move from 0, 0 to 1, 1, 1, 1, 1, 1 to 1, 1, 0, 1, 1, 0 to 1, 0, 1, 1, 0, 1 to 1, 0, 0, 1, 0, 0 to what exactly? 0, 1, 1. From here it will go to 0, 1, 0. From here it will go to this. So here it is going to this. So this is exactly this state diagram, right? This is for 3-bit asynchronous, asynchronous, okay, asynchronous up-down counter, asynchronous up-down counter. So next, what we try to do is we'll go to the next step wherein we are trying to look at how exactly it is going from one state to the other state. So we know that for 0, 0, 0, just look at this, how exactly the things are happening here. When up is 0, it is going from 0, 0. So look at this, for 0, 0 to 1, 1, 1, what is exactly happening? Next state for 0, 0, 0 is 1, 1, 1, 1, and next state to 1, 1, 1 is 1, 1, 0. This is exactly down counting. When up is equals to 0. When up is equals to 1, when up is equals to 1, what exactly happening is from 0, 0, 0 to 1, 1, 1, what is happening is up counting. For 0, 0, 0, it is 0, 0, 1. So it's gone up counting. So both up counting, down counting going up, right? So in a up counter, what we try to do is for example, we have 3 flip-flops, but in this case it is 3 flip-flops, right? So 3 flip-flops. So what is the issue that we have? The issue that we have is something like this. Either we need to connect from Q or Q bar to where? To the clock input of next flip-flop. First flip-flop we will connect a clock. All T's are equal to 1. That is not an issue. Everything is in toggle mode. Then only I will get a counter for asynchronous. But what should be the input to the next flip-flop clock? Either it should be Q input if it is up counting, right? Q bar as a clock input if it is down counting. So up counting and down counting depending on what? Up counting and down counting depending on control signal up. We have an up text. When up is 0, we are doing down counting. When up is 1, we are doing up counting. So what we try to do is, by using this up Q and Q bar, I need to get a clock input. I need to get a clock signal. Clock as an output. But it need to be applied to this. So that we will work it out. So what is that is something like this. So we have a control signal called up, and we have Q and Q bar. What I show is here, I need to build a combination circuit where the inputs are M, is not M, now we are using Q upper. So we'll write as up. One of the input is up, Q bar. Output is clock. This is need to be given to the next flip-flop. Okay. So what we try to do is, what exactly this circuit such that we will get a appropriate clock. So for that I have a input output relations. If I know input output relations, I can find the design, I can find what is there inside, what is this circuit inside. So what actually required is clock. Clock is output, which is input to the next flip. Now when up is equals to 0, what it should be? When up is equal to 0, down counting. So let's say this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, in all possible combinations. Now what we try to do is, we will try to see the things that when up is 0, what should be your clock? Your clock should be down counting, as we know, it should be Q bar. So what exactly it should be is output should be 0 1 0. When you are doing up counting, when up is equals to 1, up counting is going on. Now your output should be Q. That means clock should be applied with Q. So clock should be Q. What is this Q? Should be the clock. That means this is 0 0 1. Now these are the inputs to the circuit, and this is output to the circuit. So now what I can say is clock is a function of inputs up Q Q comma Q, right? So this is how exactly it is. Now what we try to do is, from input output relations, I take a 3 variable k-map. From this 3 variable k-map, what I try to do is, this is your Q bar, Q up. Up is equal to 0, up is equals to 1. 0 0 0 1 1 1 1 0. So what I try to do is, I will enter the values 0 1 0 1 0 1 0. Next 0 0 1 1. Now what is the combinations possible? I can combine these two. I can combine this two. If I combine this, it is the k-map for clock, because output is clock. So clock is nothing but a up bar. I am writing expression for this up bar. What exactly this? Under this is Q bar. So up bar Q bar plus for this if you look at, this is up bar Q bar, whereas this is up, and this 1 and 1. So this is 1 and this is 1. So it is Q. So up Q. Now from this expression, what I can do is, I can draw the circuit and the connection. So I'll take 3 flip-flops as usual. This is full counting. We are not stopping counting in between, but the only thing is we are choosing the mode. What is the mode? Whether it is up counting or down. So in such cases, the clears and presets are fixed. We are not going to apply any logic to them. We are not going to stop in between any counting process. So for that, it is by default. This is a preset. All are combined. Clear of all are combined and tied together, connected to one. For all these flip-flops, the input T input is 1. T input is 1. It means it is in toggle state. That means for every clock signal, it is going to change its state. Okay. Now this is fine. What I need to do is, I have an up control, but the expression I got is, here it is QA force Q bar. What I get out is QA. This is QA bar. Okay. So with respect to this, what exactly that I try to do is, so this is up bar QA bar. So here I'll take the up signal. So what I try to do is, let's take up. If you connect it to inverter, it will become up bar. So what I try to do is, I'll take QA bar and up bar. I will AND it. I will take up directly. I will take QA directly. So what I try to do is, I'll write on the top of it, just here. So what I need to do is just to take this input, give it to AND gate, then OR it, then connect it to What do? We connect it to clock signal. Okay. So this is what exactly the clock that we are applying, for which the expression is, this is here up bar QA bar when we are applying with respect to flip flop A. This will be up QA. For the next flip flop, it will be, how exactly it will be? Same thing. You take this, you take one up, connect it to inverter, you take this two, give it to AND gate, you will get one output. You take Q bar, this is QB, this is QB bar. Okay. So what I need to do is, I need to connect up, so we'll make it little bit down. Okay. What I try to do is just remove this portion. So what I try to do is, just I will complete this part. I'll take this complement, I'll connect it to AND gate. Now this is up bar QB bar. This is up QB. This we need to connect it to OR gate, then connect it to the clock. Okay, this is the clock. So clock input to B we are getting from A. Clock input to C we are getting from B. Okay. So what we have worked out is in general. Now we are applying to the case to case. What is that case to case? Clock input for B we are getting from up QA and QA bar. Clock input to C we are getting from QB bar, up and up. What I can say is, instead of working for twice, what we did is, we have worked only once and we are applying to the case. The meaning of that is, I try to show you. If you want clock to the flip flop B, clock to flip flop B is clock B. The inputs are up QA, QA bar. Okay. Now if you are applying clock to C, flip flop C, which will call it as clock C, inputs are once again up. Now this time it is QB and QB bar. Okay. So what is this circuit? We have got it already, that we have applied it. This is consisting of two AND gates, one inverter, one NOT gate, one OR gate. That is two AND gates, one NOT gate, one OR gate, as we have seen. Okay. So this is what exactly the conversion circuit capable of producing a clock. Right. So this is what exactly here it is. Okay. So this is how one can design up down pattern. Right. So what exactly that we are looking for the outputs? When we look for up counter, where we look, when we are doing an up counting, we look for QA, QB and QC. When you are doing down counter, we will be looking for QA bar, okay, QB bar and it is QC bar. This is LSB, this is MSB, this is QA, which is LSB, this is QB, this is QC, this is MS. Okay. So what I can say is QA bar, QB bar, QC bar, QA bar, QB bar, QC bar. This is to be observed for down counting. Okay, you need to observe QA, QB, QC for up counting. This is a 3-bit asynchronous up down counter full design. Done.